All right, so we'll continue our discussion about Chapter 13 by moving on to experiments. Experiments are the only way to prove a cause and effect relationship. Remember, observational studies cannot do that for us. So just so that we have a story problem to talk about, an experiment that I've never done but often thought about involves answering this question: does caffeine make teenagers hyper? Some people question, the wisdom of going and getting one of your big iced lattes right before class, right? Maybe it makes you hyper. I don't know. For the purpose of our little pretend experiment today, hyper is really hard to measure and define. However, the students that I've seen that are what I would call hyper are usually much more energetic. So I will say that for the purposes of today, we'll instead substitute hyper with increased heart rate. Right? If you've got a lot of energy, your heart is beating faster. So we're going to talk about how you would set up an experiment to answer this question. And to do that, we're going to need to define some important words so we can all have the same vocabulary here. So in an experiment, the scientists will randomly assign what we call treatments, we'll talk about that, and compare responses. So remember, in an experiment, the scientist assigns what's happening. So we'll say that Mrs. Curtis is the scientist for this experiment, so that means I get to choose who has what thing. And hopefully I'm doing that randomly, not just picking and choosing. So in our story, we're going to define some words here. We need to talk about a factor. A factor is the variable we're kind of testing out. So you want to think in terms of like your algebra class. This would be your x variable, the independent variable, the explanatory variable. So in this case, the variable that I think is changing how students react would be the caffeine. Okay? So in our experiment, caffeine is the variable I want to test, that I want to try out. The levels are like the choices, what I'm actually going to give to people. Now, it's important that I have more than one choice. I can't just give everyone caffeine and see what happens. I want to have kind of two options. So, I don't know, maybe I'll give half our class Pepsi, that has caffeine in it. And maybe I would give the other half like a caffeine-free Pepsi. And we'll talk in just a minute about why I chose those particular items. The other important variable here is my response variable. This is the one I'm going to measure. I'm looking for changes or differences. You might think of this as the y variable, the response variable. So in our experiment, if I'm checking to see if caffeine changes your heart rate, in the end, I want to measure your heart rate. That's what I'm going to compare between my groups. And then my experimental units, when they're people, we call them subjects. This is like who or what I'm experimenting on. So in our little example, if I want to see if caffeine will increase the heart rate of teenagers, I'm probably going to experiment on my students. You are all teenagers, and so you would be my experimental units or subjects. Again, if it's people, we like to refer to them as subjects. It just sounds a little nicer. All right, so there are actually 4 principles of good experimental design. I'm only going to talk about 3 of them today, but there are 4 things that make experiments really good. The first is control. Now, in your science class, you hear control, you're thinking control group, the group that gets no treatment. We need to change our thinking for statistics. When I say control, I'm talking about keeping things the same. Other variables that will not change between person and person in my experiment. So some examples might include how much soda I give. It would not be fair if one student got an entire can of Pepsi and another student got oh, I don't know, just one small sip. Okay, that's a variable, how much soda. It could vary or change person to person, but I want to keep it the same for everyone in my experiment. Another example might include location. It might not be fair if I gave all the students who received Pepsi their Pepsi in my classroom, and everyone who got the caffeine-free, I put them, I don't know, inside the walk-in refrigerator. Okay, now I've introduced another variable. Some of them are warm and some of them are cold. That's not keeping things the same. Okay, another variable might be activity level. It would not be fair if I gave the caffeine-free Pepsi students, I just left them in my room and said, just sit there, and we're going to measure your heart rate after 30 minutes. And then the kids who got Pepsi, I put them out on the football field and told them to run around. And then I'm going to measure their heart rate after 30 minutes. Well, of course their heart rate's going to go up if they're outside walking around. So that's not fair. I want to keep things the same. So any variable that I'm not testing needs to be controlled as much as is humanly possible. Okay. So certainly the Pepsi and caffeine-free Pepsi, those are different. That's because I'm testing those. Anything else, I want to make sure I keep it the same between those two groups. Very important. All right, the other two aren't quite as complicated. As you might imagine, randomize is just what you think it is. We should assign treatments randomly. If I'm choosing between Pepsi and caffeine-free Pepsi, I don't go through and pick my most hyper students and give them Pepsi. That's not fair. I would assign it randomly. Think names in a hat. That's going to be the easiest and probably the best way. I put all my students' names in a hat, and I don't know, if I have 50 students, the first 25 I pull out are assigned to the Pepsi group. As simple as that. Then the last 25 get the caffeine-free Pepsi. But that way it is random. The last principle I want to talk about is replication. This is talked about in two different ways. One, we consider replication if we do the experiment more than once. Okay. Sometimes strange things happen just based on perhaps the group of volunteers we have. So I should do an experiment more than once. We'll write this in red. The U of U once published results that they've done this amazing experiment and produced what was called cold fusion, okay, this way to get power without having to explode a nuclear bomb. So they were, whoa, we're so cool, it's amazing. And they were never able to duplicate the experiment, and they were teased mercilessly and made fun of. Believe it or not, people still talk about that. You may have not heard that story. It's quite old, but they were made fun of. So that's why we replicate our experiments. We don't want to say we have these amazing results and not be able to duplicate it. The other way that we talk about replication is that we do need to use more than one person or object in our experiment. So make sure an experiment is not just two people, one to drink Pepsi and one to not drink Pepsi. Okay, we need to involve multiple people for our results to be valid. All right, we'll continue our discussion of experiments in the next video. The last thing I wanted to talk about with experiments today was the idea of drawing a diagram. This is not considered a complete solution, but it might be a fast way to get started in your explanation. So you'll see these in your textbooks. They'll say something like, well, let's say we have our 50 students. I'm going to divide them into two groups. Remember, we had a Pepsi group and a caffeine-free Pepsi group. And then I might say something like, I'm going to randomly assign them. So there's going to be 25 getting Pepsi and 25 getting caffeine-free. Now this, I might need to go a little more in depth. So I could write, like we talked about, I was going to put the names in the hat. The first 25 I pull out get Pepsi. And then when I'm all done, I'm going to pull these people back together and I'm going to compare their heart rates. So this is just a way that could help us visualize what's happening to set up this experiment. We'll continue our discussion in the next video.